linear independence. Let's see how far I can get in 10 minutes. um, I do hope to try to cover the gist of this section. Three things. Linear independence. I think with that we have the definition for linearly dependence. And then secondly, we move to how to determine whether or not vectors are linearly independent or dependent uh, in terms of functions. So we introduce the idea of a Warn scheme. Um, and then from there, how you can use the Warn scheme to determine whether or not functions form a linearly independent set or not. Um, and we'll just look at it. Here's the definition for linearly independence. A set of vectors v1 to vr in some vector space, capital V, said to be linearly independent. You need to know this, and you have to be able to say this, write this definition out on the test. The whole statement is important. If there exists scalars, k1, k2 to kr, such that the linear combination of those vectors and the scalars equal to 0 implies that all the scalars are all 0. That's linearly independence. Secondly, on the test, I will ask the question for linearly dependence. Set of vectors v1 to vr in some vector space is said to be linearly dependent if there exists. It's the same premise, the same setup. If there exists scalars k1, k2 to kr such that the linear combination of the vectors and those scalars equal to 0 implies not all the scalars are 0. The conclusion is different. The conclusion is different. So the premise argument for both statements, they start the same, but they conclude differently. Now what is that saying? For linearly independence first, if we could write that out in English, what they're trying to say is that the vectors that exist within that particular space are linearly independent if no vector can be written as a scalar multiple of the others, because all the scalars go out to be 0. Right? K1 to kr are 0. But if those scalars are not all 0, which is the case for linearly dependence, if those scalars are not all 0, then it's not all 0 for the scalars, and it's possible to take one vector here, one of these vectors here, like v1, v2, or whatever, v5, and you can write that vector as some scalar multiple of the other vectors. So you must give me both definitions the way I state them here. Some books would give the definition for linear dependence by saying the set that's not linearly independent. Well, obviously that is true, but this is what I want here. Okay, so if you write that simple mumbo jumbo stuff, then I'll just put an X on that. All right? So you must say this. So let me see if I can write that out quickly and then look at some problems. Vectors are said to be linearly independent if no vector in the set, the emphasis is on no, in the set, can be written as scalar multiples of the other vectors. That's what this conclusion is trying to get at. Here and I post this today in Blackboard. So for linearly dependence, for vectors that are linearly dependent any vector in the set can be written as a scalar multiple of the other vectors. Here's a very important theorem that kind of helps us with some of the questions where they ask you to solve by inspection whether or not a set forms a linearly independent or linearly dependent set of vectors. Let S, capital S, be the set of vectors that goes from V1 to VR, be a set of vectors in Rn. And this Rn is the nth Euclidean vector space. If R is greater than N, in other words, when you talk about Rn, you're talking about a set of vectors such that the terms inside V1 all the way to V sub n. It's like the idea, right? This means that this is a vector that has n tuples. So here, R denotes the number of vectors that I have given in a set. R denotes the number of vectors. If R is greater than n, if the number of vectors is greater than what the space set allows for a vector to have components in, if R is greater than n, then the set is said to be linearly dependent automatically. If R is less than n, then it's impossible for those vectors to span the big space, R to the n. Right? If S contains at least two vectors that are scalar multiples of the other, I told you that defines linearly dependence, then the set S is said to be linearly dependent. If I can take one vector and write it as a scalar multiple of another vector, basically the vectors will cancel out. Right? So you get dependence. I can take one and cancel out something else. I get linearly independence is if no matter what kind of combination I have with the vectors, they cannot cancel out another vector. Right? They say to exist independently on themselves. Right? This vector does not need vectors 2 and 3 to be written out for it to represent him. He represents himself. There's no combination of the vectors that can give you that vector, linearly independence. Right? The Warn scheme helps us. If you have functions to determine whether or not the vectors form, here the functions form a linearly independent or dependent set. The Warn scheme makes use of the derivatives of the function and also the determinant. So given some functions here, f1 to f sub n, we say that here, if this determinant of functions, now each column starts off with the function and then below it you take the derivative. So here this is f sub 1, f sub 1 prime, f sub 2 prime, all the way down to the n minus 1 derivative. And so you only declare that these functions are n minus 1 differentiable because that's all the derivatives that you're going to be taking. If I have 5 vectors, then you're only taking 4 derivatives. That's what they're saying. Write this as a determinant. If the determinant is not equal to 0, then we say that the set of functions are linearly independent. Right? So it somewhat goes with the determinant of a regular matrix not equal to 0. That's added, you remember, into the monster theorem, right? So here the Warn scheme basically marginalizes that particular criteria for the determinant not equal to 0 for the monster theorem. Now, these problems by inspection 4 of them. If you give me a couple of minutes, we can just state what's happening here, and then I'll be done for today. Can't get any further. Explain why the following form linearly dependent set of vectors solved by inspection. They're making use of this theorem up here. They're making use of that theorem that has 3 components in it. Okay. So here, part A, notice that u sub 2 is a scalar multiple of u sub 1. That's linearly dependent, right? The vectors are scalar multiples of each other. Can't have that. Here, part B, I have 3 vectors, but the space allows for 2, R2, right? Go back to the theorem. By the theorem, if R is greater than N, then the set is linearly dependent. Here, R is equal to 3. I have how many vectors? 1, 2, 3. Right? R is equal to 3. N is equal to 2. By the theorem, R is greater than N, linearly dependent. Right? Part C, P2, P sub 2 is a scalar multiple of P sub 1. Polynomials scalar multiples of each other. It's this last one here. Part D. If you look at matrix A and matrix B, well, they differ by -1. So they are also scalar multiples of each other. And so they would be linearly dependent. Let me stop there. I'll finish this section on Monday, and then we'll get into 4.4, try to cover 4.4 and 4.5 as well. And don't forget the test. You got the email or the announcement in Blackboard. The test will be available for you in the testing center after Wednesday. So you can take it Wednesday afternoon, you can take it Thursday, you can take it Friday. I will have to cover, as you saw in the announcements, I will have to cover the next section for the next test on Wednesday, okay? But I give you any one of those days, Wednesday, Thursday, Friday, to take your test in the testing center. Thank you.